Well, see, in this lecture, I will discuss about oxo salts, their preparation, their solubility, their stability, and after that, lattice energy. I will role of lattice energy and hydrogen energy in the stability. So first, I will take up the simple preparation of these kind of salts. So one very simple preparation is that if you take alkali, means NaOH or KOH or metal hydroxide, first group metal hydroxide, and acid, you can take acid. Like for this, you can take H2CO3. In place of H2CO3, you can take carbon dioxide directly also. And this nitrate, for nitrate, you can take HNO3, and for H2SO4, I mean sulfate salt, you can take H2SO4. Bicarbonate, I think directly to prepare bicarbonate is relatively difficult, so we can prepare this indirectly. Means in the preparation of carbonate, when you pass carbon dioxide for longer time, you will get bicarbonate, and it is a very old story, all of you are knowing. So metal hydroxide, if you take these metal hydroxides are solid at room temperature. If you take carbon dioxide gas, so you will have metal carbonate M2CO3 plus. This is also solid, but it becomes aqueous because water is formed here, right? So you can balance this to MOH. Or alternative, you can use MOH aqueous plus CO2 aqueous, or you can write this CO2 aqueous, you can write H2CO3, right? So on this reaction with this, you will have M2CO3 plus H2O, right, to MOH. So this carbonate, and if you pass carbon dioxide longer time, then this carbonate is converted into bicarbonate. So M2CO3 plus H2O aqueous plus CO2, this will give MHCO3 whole twice, right? So 2 MHCO3 whole twice. So these are the simple methods you can use to prepare carbonates, right? And bicarbonates, all bicarbonates. Oh, what I have written here? MHCO3 MHCO3 and 2MHCO3, right? Okay. All bicarbonates, all all means all, not only this first group, second group, or whatsoever, right? All metal bicarbonates, on heating, on mild heating or gentle heating, on mild heating, converted into corresponding carbonates. So you can prepare any metal carbonate, MHCO3, you will give M2CO3 plus H2O plus CO2, right? So these are the simple reactions and very useful reactions. So if you can see, this reaction is basically reversible. Yes, this reaction is reversible, and this equilibrium shifts, depends on the concentration of carbon dioxide. If you increase the concentration of carbon dioxide, this equilibrium shifts forward, and there is a role of pH basically here, right? So on heating, all metal bicarbonates on heating they produces corresponding carbonate, right? Now see if it is given like CaHCO3 whole twice, so you will have CaCO3 plus H2O plus CO2, right? So you can take any metal, all metal bicarbonates without any exception. Okay. Now see, this is all about carbonates and bicarbonates. Now see nitrates. So you can prepare nitrates by the reaction of alkali with nitric acid. Alkali means metal hydroxide MOH plus HNO3. You will have MnO3 plus H2O, right? And this metal nitrates are always soluble. Nitrates of all metals are soluble. You can write straightforward that nitrates of all metals are soluble in water, right? So in this way you can prepare the metal nitrates. One more method we can use here to prepare nitrates, that is indirect method, that if you take metal carbonate of this group M2CO3, if you take metal carbonate, and this metal carbonate if reacts with HNO3, then also you can get nitrate. MnO3 plus H2O plus CO2, right? And all these reactions I have already explained in various lectures. I used to say, see, this is a normal salt, or you can say normal salt, and this negative reaction of normal salt with acid, all of you are knowing that if you react this normal salt with acid, which is stronger than the negative part of the salt, is formed. So this negative part of this salt is formed by the carbonic acid, which is weaker than HNO3. So you can very easily get this reaction, right? So HNO3, you can prepare metal nitrates by this method also. So this is one method, and this is second method. Now you can directly prepare nitrites also. You can prepare here nitrites, and preparation of nitrite is a little bit tricky. So see, nitrites, for nitrites you can take you can take metal nitrate of this group, metal nitrate, and if you heat, so this will convert into corresponding metal nitrite plus oxygen, and here M is equal to Na, K, Rb and Cgm. So all these metal nitrates on heating they converted into corresponding metal nitrite and oxygen gas. Remember, this is very important reaction. And here in this list there is no lithium. So what about lithium? So if you heat lithium nitrate, this will decompose basically into lithium oxide plus NO2 plus O2, right? So this is exception. Exception of this first group. Exception of first group. All first group metal nitrates on heating gives corresponding nitrite and oxygen except lithium nitrate. right? So this is one method of the preparation of metal nitride, that you can heat the first group metal nitrates and get the metal nitride. One more method you can use here, that if you react this KOH with NO, so KOH on reaction with this 4NO and 2 KOH, so you have KNO2 plus N2O plus H2O. And if you take larger molar ratio of this, means if you take here 6NO, then you will have KNO2 plus N2 plus H2O, right? 4 KOH. So if you change the molar ratio here, 2 to 4, 4 to 6. So in this situation, you will have N, right? So this is preparation of nitrides, preparation of nitrates. Now see sulfates. Sulfates, same method. You can use alkali. Alkali means metal hydroxide and H2SO4. So you will have Na2SO4 plus H2O. And indirect method you can use carbonate, metal carbonate plus H2SO4. So the same concept, that this carbonic acid is much weaker than H2SO4. So this will replace this from here, and you will get the salt of a stronger acid, right? So M2SO4 plus H2O plus CO2. So here I should write M2SO4, not and all the metals you can take here, right? So this is the preparation of sulfates. Okay. So see, in these oxo salts, one very important point here, that the salts of lithium and sodium, they are hydrated, right? Salts of lithium and sodium are hydrated. Very few salt, I think one or two salt we have that potassium, they are hydrated, otherwise no salt of potassium. But lithium and sodium salts are usually hydrated. And few of potassium also hydrated. But for rubidium, cesium, no hydrated salt. Rubidium, cesium, no hydrated salt. Right? So this is an important point. See, extent of this hydration is basically depends on the size. If the size of cation is large, so salt is formed, but not a hydrated salt. You won't get a hydrated salt much for the larger size cations. One more important point I would like to mention here, that if you are talking about the mixing of metals with each other, means what you have lithium, sodium, potassium, rubidium, cesium. So if we are talking about the mixing of, because since I have discussed here the size, mentioned here size, so there is one more important point is here, and it is applicable in the whole chemistry, that if the size of metals, it is comparable, this is not a large difference if in their atomic size, then only they mix with each other. So lithium and sodium, they can mix with each other, and form alloy. So alloy formation is also, accompanied with the comparable size metals, right? If there is a large difference in the size, then you won't get alloys. Suppose that if you are talking about the lithium and cesium, and if you mix these two metals and say, okay, this what we are getting this alloy or homogeneous mixture. No, you won't get the homogeneous mixture. So alloy formation or mixing of metals, that is also controlled by the size, right? So mix with each other and form alloy due to comparable size, due to comparable size. Okay, so this is hopefully it is clear to all of you, right? Now some more important properties of this carbonates and bicarbonates, some properties. See, carbonates are basically stable. Carbonates of group 1 metals are stable, right? Means not easily decomposes into corresponding metal oxide and carbon dioxide, right? The except one exception is there, means suppose that MCO3 is there, so this is stable, thermally stable if M is equal to Na, K, Rb and Cs, right? But lithium, exception is lithium. Exception is lithium. If you take the lithium carbonate, Li2CO3, so this is decomposed and you will get lithium oxide plus carbon dioxide, right? So basically this carbonate ion, if you see the structure of this carbonate ion, this is the structure of carbonate ion. So what is happening here, that on heating this bond will move like this bond is moving like this, so you will have carbon dioxide, a good leaving group, plus O2 minus, right? So basically this is the mechanism of the decomposition of carbon dioxide, carbonate ion, right? So lithium carbonate, this on heating decompose, but carbonates of sodium, potassium, rubidium, cesium, they do not decompose on heating, right? So this is very important. And see, group 1 metal, due to their basic character, they also form the solid bicarbonates, right? So solid bicarbonates are known for the first group metals. So we can also mention this point. Group 1 metals form solid bicarbonate carbonates, right? And none of the other, right? No other metal can form the solid bicarbonate. So you have solid bicarbonates only from this first group metals. So metals from group 1 metals form solid bicarbonates. None of other metal bicarbonate is solid. is solid, right? And so you have MHCO3 solid first group, where M is the first group metal, right? And one more solid bicarbonate is known as ammonium bicarbonate, but this is not a metal bicarbonate. This is also known. So clear to everyone. So group 1 metals form the solid bicarbonate, and in the whole periodic table you will not get the other any metal bicarbonate which is solid. That is always exists in the liquid phase. Right? Now, see. So group 1 metals form the solid bicarbonate, and one exception that is always there, that is lithium exception, lithium bicarbonate LiHCO3, that exists in solution, not in solids, right? See, sodium bicarbonate, if you see sodium bicarbonate NaHCO3, this exists in this bicarbonate unit exists as a polymeric chain. So in this, the bicarbonate unit exists as a polymeric chain through hydrogen bonding, right? Through hydrogen bonding, like this. So this is hydrogen bond, right? And potassium bicarbonate KHCO3, in this bicarbonate unit acts as a dimer, right? So this is polymer, and here the bicarbonate unit acts as a dimer. And this is also hydrogen bonding. So this is dimer. So potassium and sodium bicarbonate, in both the cases, the bicarbonate unit exists as a, joined together with a hydrogen bond. This is very important question, right? Now see, this all the carbonates and bicarbonates are soluble. See, they have relative solubility, different relative solubility, but all are soluble. So all the bicarbonates and carbonates of group 1 are soluble in water, right? Except lithium carbonate Li2CO3 and NaHCO3. So these two are insoluble. lithium carbonate, and this sodium bicarbonate. This is very less solubility. Means if you compare the solubility of potassium bicarbonate and sodium bicarbonate, so where the sodium bicarbonate dissolve 6 grams per 100 ml, so that potassium bicarbonate dissolved 100 grams per 100 ml, 100 grams per liter, and it is only 6 grams. So you can say this is very moderate soluble sodium bicarbonate. So you can say this is insoluble, right? So this is all about the carbonates, bicarbonates, and I will discuss this solubility of all these in a different heading, that is in the lattice energy and in the uh, hydration energy in terms of, right. So I will again take up all these things, but this is exceptional, so I have explained this here. Now solubility and hydration. Solubility and hydration. Solubility and hydration. So this is a thumb rule for the solubility of basically ionic compounds in water, that delta H hydration or delta G hydration, that should be greater than delta H lattice. Delta H lattice means, in a simpler note, you can say that the hydration energy if greater than lattice energy, then the salt is soluble. So this is the thumb rule for the solubility of ionic crystals, right. Now see, lattice energy lattice energy, this will varies with R plus R minus, means radius of cation and radius of anion. And hydration energy, if you see, so you will get hydration energy, basically it is the 1 by R plus and 1 by R minus. Why I have separated these two? Because hydration is basically a individual phenomena, means this is defined in when the ions are separated from each other, well separated, right, in aqueous medium. And this lattice energy, it is the single system of cation and anion. So it is a single system, so with the variation of this distance between cation and anion, this lattice energy depends on that. So, and it makes the difference in the magnitude of this lattice energy and hydration energy, right. So you will find that the lattice energy, suppose that if we are talking about this first group metals or first group metal salts, so if you can see that down the group, the lattice energy decreases for most of the salts, whether it is chloride, bromide, fluoride, or in all cases your lattice energy, that is decreases down the group, right. This is decreases down the group, all the lattice energy for all the metal ions. So see, the lattice energy in this group 1, if we compare, the lattice energy decreases lattice energy decreases down the group, down the group, right? For all kinds of salt, whether it is fluoride, chloride, bromide, iodide. If you take any kind of salt, then lattice energy decreases down the group, right? And hydration energy, or hydration gives energy, hydration is also decreases, right? So hydration energy also decreases down the group, down the group. So you can compare this with this, relation. As you move down the group, size of cation increases. So if size of cation increases, suppose that we are taking single anion, suppose that we have taken fluoride, right? So fluoride is common. So this hydration energy with respect to the fluoride, it is common for all the lithium, sodium, potassium, rubidium, cesium, every for everyone it is same. So the variation will come from here. When you move from lithium to sodium, sodium to potassium, potassium to rubidium, so hydration enthalpy or hydration energy that will decrease due to the increase in size. Similarly, here this size of R minus is fixed, fluoride is fixed, so the variation will come due to this. So lattice energy and hydration energy both decreases down the group. It is clear. So how to predict the solubility? If both were decreases down the group, so this is a very important point. So solubility, basically solubility increases down the group. This is very important point. Solubility increases down the group, when lattice energy, when lattice energy changes more. Changes means decreases more, you can say. Decreases more than hydration energy. More than the decrease of hydration energy. Decrease of hydration energy. Right? More than the decrease in the hydration energy. Clear? Now, second case, the solubility decrease down the group, when hydration energy or lattice energy decrease, less decrease in the lattice energy compared to the hydration energy, right? So down the group, solubility decreases down the group, that the lattice energy changes less, lattice energy decreases less, uh, but free energy, I mean hydration energy changes more, and hydration energy changes more. Now see one example. Try to understand this statement with one example. See, if you take lattice energy for delta H, lattice change of this lattice delta of lattice energy, I should write here, lattice energy from NaCl to KCl. When you are moving from NaCl to KCl, means down the group, you have the value 67 kilojoules per mole. Means the lattice energy of sodium chloride minus the lattice energy of potassium chloride. If you subtract these two values, you have 67 kilojoules per mole. And delta of hydration for NaCl to KCl, this is 76 kilojoules per mole. Now see, down the group means when you are moving from NaCl to KCl, the decrease in lattice energy is less. Decrease in lattice energy is less, and decrease in hydration energy is more. Decrease in hydration energy and decrease in hydration energy, decrease in hydration energy is more. So the solubility decreases. So you can say from here that KCl is less soluble than NaCl. Right? So it is clear to everyone. But every time you won't get the questions based on so logical data and all these things. You will get the question in our exams straightforward, that arrange the following in the increasing order of solubility or decreasing order of solubility, like that. So for that purpose, we have to some simple concept. So the simple concept is, you can write here that the solubility of most of the salts of group 1 decreases down the group. That's it. Right? So suppose that if it is given chloride, bromide, iodide, right? So if it is given like MF or MX, we can say MX, LIX, NAX, KX, RBX, CSX. So we have taken halogen salts, and here X is equal to, you can take Cl, Br and I, right? X is equal to, you can take Cl, Br, I. So it is decreases down the group. So the most soluble you have this. But here you cannot take fluoride. Here you cannot take fluoride, right? Because fluoride is exception here. So in most of the cases, you have this trend, this order. Like if you take sulfate, then also have same nitrates. All nitrates are soluble, and there is no question of nitrates, right? So this is the solubility. And what is the exception here? So exception you can note down. Exception is fluoride, carbonates, hydroxide, right? Carbonate, hydroxide, and oxide also. So here the solubility increases down the group. Down the group. Right? Clear to all of you? So this will help you to answer the straightforward question which is asked in your exams. Right? Not much logical questions you are going to get, but sometimes you may get that this lattice energy data is given, hydrogen energy data is given, and you have to predict the ion solubility like that, right? So if you take Li2CO3, Na2CO3, Na2CO3, K2CO3, Rb2CO3, Cs2CO3. So the solubility increases down the group. Solubility increases, right? So this is the order of solubility. So hopefully all of you are clear in this regard that how this solubility of this carbonates, fluorides, because they are smaller ions and they follow this criteria that the down the group lattice energy decrease is more than the decrease in the hydration energy, right? So you can easily explain this, right? Now we'll talk about some thermal stability, right? Now see, thermal stability, if we do one more thing, thermal stability. Thermal stability. So, thermal stability, we can correlate thermal stability. Thermal stability. It is directly proportional to, we can correlate this with negative of delta H formation of the salt, right? Means more the enthalpy of formation, more the thermal stability. But every time, and you should see here negative value, right? But every time you won't get the question in which this value is given, again you have problem. So again I will simplify that problem, your problem, but I am giving you the concept. And also you can correlate this with the polarizing power and polarization of the bond between them. But that is not the sole reason, we can say, because sometimes it is happening that when we are heating certain substances, due to the formation of certain more stable species from the substrate, the salt will decompose. So that is not also always, but we can correlate that also with the covalent character and polarizing power of cations and anions. Good correlation, no problem, right? So we can correlate. But if you see in the 2 point, I can explain many of salts thermal stability. So if you take nitrates, if you take carbonates, if you take sulfates, if you take bromides, if you take iodides, if you take OH negative ions. So salt and compounds of these anions, compounds of these anions, thermal stability increases down the group. This is very important point. Down the group. Thermal stability of these anions in group 1, right? So if you take any compound of this, and the thermal stability will increase. Suppose that it is given Li2CO3, Na2CO3, K2CO3, Rb2CO3, Cs2CO3. Although all these are thermally stable, right? But relative stability basically that is increases down, right? Similarly, if you take nitrate, sulfate, chloride, bromide, iodide, hydroxide, right? Suppose that if you take an LiOH, NaOH, KOH, RbOH, CSOH. So this is the thermal stability order, right? So likewise, now you can make the order of salts of these compounds thermal stability. Hopefully, it is clear, because we do not require to give more reasoning, but reasoning is here I have written. And one more thing you can say, that since these are the relatively large ions, so down the group the size of cation increases. So if the size of cation increases, so they have more ionic character. So you can correlate this with the ionic character. So ionic character increases down the group, right? So if you want, you can correlate this with ionic character. Now, exception of this point, the exception of this point is, exception you should remember, fluorides, right? The thermal stability of these, thermal stability decreases down the group, right? So if you take LiF, NaF, KF, RbF, CSF, right? So the thermal stability is varies like this. Suppose that if you in a series, if you take this LiF, LiCl, LiBr, Li. Suppose that this is given. So if you want to decide in this case thermal stability, so you have to apply the concept of polarization. See, lithium is common in all, so leave that lithium. Now you can see here F minus, Cl minus, Br minus, I minus. So such type of questions you can easily answer. How? Now, which one is the largest anion? The largest anion is this I minus, which has maximum polarizability. So this has maximum covalent character. So obviously the thermal stability is here. This is maximum covalent character. Maximum covalent character. Right? So this way you also can answer the questions, right? So this is the thermal stability of different salts of group 1 metals. Okay.